Hello again, Owen. This is me, Mr. Rao, back again to share video. This video is on 1.16 and 1.17, which was our last quiz of the semester. The basic three main topics that we are going to be going over would be synthetic division, excuse me. The main purpose of that is to find and / prove zeros of a function. Prove zeros of a polynomial function. The second thing is long division. That's polynomial long division. And the reason behind that is it gives us the equation of slant asymptotes and also asymptotes. And another way we could say that is equations for end behavior. And the last part is to just a big overall review of polynomials and also rational functions. So that's our goal here. I'll just skip through as many of these problems from the two sections that I think are most important here. So when looking at this first problem, what we were looking at is first finding the degree. And if the degree was n, it was noticing that when we're at least looking at possible number of each of these, what we find is that in the first case we have n minus 1 possible extrema, and there's always going to be n zeros. That's not even possible. There's always going to be n zeros. So in this first case, that means that this would be 3, 2, 3. In this case, that would be 4, 3, 4, 3, 2, 3, and 4, 3. The last one is 4. Now, not all of these are always going to show up because, at least in zeros, some of them are going to be real zeros, and then there will be pairs of imaginary or complex. Let's use complex zeros. Those are ones that have I in them, and I said pairs because if there's one, there's always going to be two. In some of these, you might graph them, and you might only see that there might be one, or there might only be two, or one, or two. And that's because there might be a pair of complex. Not always the case. You're going to have to graph them to find out whether or not they are. Important part there, though, is that when we're talking about possible amounts of each, you're going to have n minus 1, which means whatever the degree is minus 1. Amounts of extrema. Again, as a refresher, extrema is relative minimums or maximums, relative mins or maxes, and then zeros are obviously those are the values of x that make y 0. They are also x-intercepts if they are real. Otherwise, if they're complex, we call them zeros along with real ones. So this one says, graph the following on paper. Describe the end behavior of the polynomial function using limit notation. Now, we don't really need to graph this. What's important is a chart. I've made this chart before, and it tells us a lot about the function. So I'm going to zoom in here to do this. We have odd functions and even functions. This is all about the degree of the degree of the polynomial. So for instance, if I had x to the 4th plus 3x squared plus x, that would not be odd, so I got to add another one in here. X to the 5th, now it's odd. In this case, let's go back to that example. This would be even. In terms of this, positive and negative we're talking about the leading coefficients. So a positive leading coefficient would be something like 3x squared plus 5, where negative 1 would be like negative 2x cubed plus 6. So this would be negative there. So what happens is, depending on each one of these things, we fill out a different graph. So if it's an odd positive, it starts off into the negative and ends up positive. If it's odd negative, that is flipped, so it starts off positive, ends negative. Even if it's positive, starts and ends going to positive infinity, and negative, they would both go down to negative infinity. So just with that chart, we can fill out all of these. This first one is odd positive, this is even positive, so the limit as x approaches positive and negative infinity, f of x is equal to positive infinity, because they both go upwards. That's this one right here. The next one, that's odd negative, so that would be the limit as x approaches plus or minus infinity, f of x is going to be, they're going to flip, so that'd be negative plus infinity. What that means is, for positive infinity, it goes to negative, and for negative, it goes to positive. This next one is odd because of this one right here, and positive, so that's limit as x approaches plus or minus infinity, it goes to plus or minus infinity, meaning it stays. If it's negative, it goes to negative, and if it's positive, it goes to positive. The last one's negative even, so that's the limit as x approaches negative infinity, f of x equals negative infinity. So in both cases, plus or minus infinity, the y value goes downwards towards negative infinity. All right, now let's talk about factors. So the factor of each problem is just the different ways to, like when we factor a problem, it's all the things multiplied together. So the factors in this case would be x minus 2 and x plus 1. This would be x and x minus 3. This would be x and x minus 2. This would be x minus 1 and x plus 2. Those factors give us a direct connection to the zeros of the function. Okay, so if one of the factors goes to 0, then the whole function goes to 0, because 0 times anything gives us 0. So that means that we had zeros at 2 and negative 1, 0 and 3, 1 and 2, 1 and negative 2. Yep, that should be a 0 here. Okay, so I just get that by, what makes the value to the left 0. Describing the function on whether or not it crosses through 0 or bounces. So I don't like to use touches, I say bounce. Let's skip this one for now. We'll go to multiplicity and then come back. So degree of a multiplicity. Degree is what is the degree of each function or the multiplicity. So looking at each one, for a, that goes to the third power here. So that would be 3. The next one, x plus 1, that goes to 2. That would be 1 for x. X minus 3 is 2. X cubed is 3. X minus 2 is 1. X minus 1 is 3. And x plus 2 is squared. Okay, so these degrees or multiplicities of each 0 or factor also tell us whether or not it's going to bounce. So basically we have 3 options. If it is a degree or multiplicity of 1, when it crosses the x-axis, it's going to cross linearly. If it has a degree of 2, then it's going to bounce, meaning that it's going to hit the x-axis but then go back in the same direction, almost like it would. This is a cross technically as well. Like it would an x squared. And then the last one, if there's degree 3, it would cross cubically, which is another way of saying it crosses. So it would look like a cubic function when it crosses. After that, it just goes between bouncing and crossing cubically. So each odd, it crosses, and each even, it bounces. So this is a bounce because it's even, and this is a cross because it is odd. So that's the biggest thing, is cross means that there's an odd multiplicity, bounce means that there's an even one. So looking across at each one of these, this would be a cross, bounce, cross, bounce, cross, 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 bounce. Again, each one has a correlation to how many multiplicities does each factor have. All right, so it's great if it is already in factored form. Sometimes though, what we're going to need is to have it, we won't have it in factored form and we will need to put it in factored form. And to do that, we need to learn how to divide synthetically. First thing to note about dividing synthetically is we cannot divide it if our denominator is x squared. It can only be done if it is linear. So this is quadratic in the denominator, so we cannot synthetically divide this. Instead, we will go over here and synthetically divide this one. We can synthetically divide this one because this is linear. Okay, so anytime we are dividing by something linearly, we can synthetically divide it. Now, what's important to note here, when we divide something, the question that you're asking is what is the zero of the denominator here? So even though we are dividing by x minus 3, what we're going to put up in the corner is 3 because that's what would make the zero, that's what would make the denominator 0. Once we have that, we're going to put the coefficients 2, -7, 4, and -5 up there. I got them from 1, 2, 3 right here, those values. Put a little line there. How this works is I drop the first value, which would be 2. I multiply the 3 times 2 to get 6. Then I add. So I add down, I get -1. 3 times -1 is -3. When I add there, I get 1. And when I multiply 3, I get a remainder of -2. The last value here will always be your remainder. And then you work backwards from there. So this is your first term, this is your x term, and this would be your x squared term. So I have 2x squared plus -1x plus 1 with the remainder of -2 over what was x minus 3. So that is how I synthetically divide a function there. Now, what would be great is if we had one that went to 0. If one goes to 0, that means that it's an even factor and we can factor it out. So that's a brief intro to synthetic division. I'm sure we'll do it again. Now, long division does the same thing. It's just in a different format. Think of it just like you would long division in a normal problem. What I think would be helpful here is actually to do the same problem as a long division problem. So to do that, I'll use this in green. We put x minus 3 on the outside, 2x cubed minus 7x squared plus 4x minus 5. And we would divide. I would ask myself what number multiplies to x minus 3. That gives me 2x cubed, and that would be 2x squared. That's because when I take this and multiply it back into x minus 3, what I get is 2x cubed, which I was looking for. I need to also multiply the -3 now. When I do that, I get -6x squared, subtract, and I get -x squared plus 4x. I drop the 4x and play the same game again. This would be -x times x would give me -x squared, but when I do that, I get positive 3x. I subtract and I get x. Drop the -5. That comes down. And my last step would be, that would be 1. When I do that, that's x minus 3, and I subtract those. X minus 3 would give me -2. So that's my remainder. And as you see, I get the same solution as when I did synthetic division. Again, here's just one example. I'll actually go ahead and go back to A, and that will be our second example of long division. So in this one, it's a little bit different, and that's because we have an x squared term. So we got to be careful the way that we line up all of our values here. So I have 2x to the fourth minus 3x cubed plus 9x squared minus 14x plus 7. It's x squared plus 4. So the value that makes that I multiply 2x plus 4 by to get 2x to the fourth would be 2x squared. So 2x squared times x squared gives me 2x to the fourth. I leave a blank here because there's no x term, and then 2 times x squared will give me 8x squared. It's important to note that I do continue to make sure that all of my numbers are lined up in order of their degree. So I subtract that, I get 0. That's negative x cubed. That's 1x squared. And I'm going to drop down my minus 14x. Next step would be, how would I get there? That'd be negative 3x. That gives me negative 3x cubed down here. 0 for that middle term. And then I get negative 12x. I subtract, and I get negative 2x. I get 1x there. That's x squared, sorry. And I drop down my 7. So here's my last one. This is going to be a 1. 1 times x squared. There's 0. And that's 4. When I subtract, I get 3. Negative 2x plus 3 is my remainder. And that is my quotient. Great. So there's another example of long division. The important note there was that sometimes you will have zeros in there to keep as placeholders. We're going to skip through some of these. An important one here is using synthetic division to describe a function and how it can be graphed. You're going to see this again. So using synthetic division here, they're quick and easy ones. So it's just 2 and negative 1. The 0 here would be negative 3. To multiply down, I bring that one down, that's 2. When I multiply, that's negative 6, and I add those, that's negative 7. So that's 2 with a remainder of 7. I would write that as 2 plus negative 7 over x plus 3. Now what's very interesting about this is a function that we can use to relate it back to transformations. It looks a lot like 1 over x. Now 1 over x is a basic function, what we know. But if we do a few things to it, we can make it look like this. If we add 2 to it, which is like going up 2, and also add 3 to the function, which is the same thing as moving it to the left 3. So that's up 2, left 3, and finally multiplying it by negative 7 would be both a flip on the x-axis and a vertical stretch of negative 7, or excuse me, of 7, just 7, since we already flipped it. So those 4 things can make 1 over x go and look like that. This can happen again on each one of these. Let's just do a few more here. I'm going to synthetically divide out 1. That's the 0 in the denominator. My coefficients are 3 and negative 2. I drop the 3 down, multiply by 1. That's 3. When I add that, I get a remainder of 1. So what this is 3 plus 1 over x minus 1. This is the same thing as 1 over x, but I do 2 things to it. It is right 1 and up 3. Great. C. Same process again. My 0 is negative 4. Negative 2 and 5 are my coefficients there. Make sure that negative 2 comes first because it's got an x. And drop down the negative 2, multiply, get positive 8, add 13. Okay, so this can be written as negative 2 plus 13 over x plus 4. That's our remainder. This would be down 2, left 4, and a vertical stretch of 13. Lastly, this last one, let's see, I have a 0 of 5, that'd be negative 3 plus 4. And when I do that, I get negative 3, negative 15, negative 9. So my remainder is 9 there. Put that over x minus 5. So this would be down 3, right 5, and vertical stretch of 9. So that's that. Pretty interesting that we can take synthetic division and use it for something else, like turning it into something that is usable with transformations. Okay. To reiterate, one other way that we use synthetic division again, though, is to find and prove zeros. So to do that, I'm going to give you a function here. This is not on the page, so it might be helpful for you to just write this down. 3x cubed minus 14x squared plus 3x plus 20. Now, when this is the case, what we are doing is checking to find the zeros. If I was to graph this, this is a very rough sketch. I'm going to get something that looks like this, and it's going to go through the point -1 here. There's a 0 there. There's another point here that I don't know. And then the last one would be happening at 4. So if we were just looking at a rough sketch, a question might be, hey, I know 2 of the zeros. What is the third one? And the reason why we know that there's 3 zeros is, one, we can see it graphically, but another big thing is the degree is 3. So remember, however many the degree of the polynomial is, that's how many zeros there are going to be. So to set this up, what we would do is we would first divide out the ones that we do know. So I would start off by dividing 4. I'd put my coefficients out front here. That is 3 and 20. And first step would be to drop the 3, multiply by 4, and get 12, -2, -8, -5, -20, 0. That's a good mark. I briefly mentioned this earlier. If we get a 0, what that means is it is a even division. It divides evenly. So we could say that x minus 4 is a factor of this. So I could write x minus 4, and what I'm left with is this right here, which is 3x squared minus 2x minus 5. And that is the same thing as, when I multiply these two out, as what we originally started with, which is 3x cubed minus 14x squared plus 3x plus 20. From there, what we need to do is now take this number and factor out -1. Instead of factoring it out from our original one, we're just going to divide it out from the one that we already have here. So this would turn into, when I drop the 3 multiplied by -1, that gives me -3, and when I add those, I get -5, which gives me +5, 0. So again, that 0 marks that I'm good. So this would be x minus 4. I've now factored out an x plus 1 because of that -1, 0, and what I'm left with is 3x minus 5. So that tells me that my 3 zeros of this function are 4, -1, and the one that I missed, if I set that equal to 0, would give me 5/3. So this one's 5/3 here. So we can find sometimes our missing zeros, or another instance is you might be doing this same process and you might have a quadratic when you're done. So for instance, let's say I was going through a whole bunch of stuff and at the end I got 204. No, that's a bad one. How about 102? That's a good one. What that means is that x squared plus 2 with a remainder of 0 is what's left. And if I were to solve that equal to 0, you would notice, hey, there's not a real number that works there. What this is -2 is equal to x squared. So x is equal to the square root of -2 plus or minus, which would be the same thing as I square root of 2. So sometimes you might get something that is not real at the end there, and that's how we would find them, because you won't be able to find them on the graph. These 2 zeros will never show up on the graph, which is why sometimes that's just what we fall into. So that's 1.16. Let's move on now to 1.17. See if I can quickly add this in there. All right, here we go. Here is 1.17. This is known as a deep dive. Basically, what we are doing here is we are reviewing polynomial functions. We're doing everything from vertical asymptotes to horizontal asymptotes, removal discontinuities, xy intercepts, domain range, and end behavior. This is a review of lots of what we've done before in this class, but we're putting it all together under one roof here. So what this looks like. Let's go through each one of these. A vertical asymptote is when you have a 0 in the denominator. You have a 0 in denominator, but not numerator. So if you have a 0, but that's in the numerator, denominator but not 0, you're going to get a vertical asymptote. So in this case, we are at x equals 7. That is a vertical asymptote. Okay, we're going to need to factor this for me real quick. This is x plus 5, x plus 2. This is x and x plus 5. This is going to be x plus 3, x minus 3. This is x minus 5, x, no, sorry, x minus 4, x minus 3. And this last one is x plus 3, and then the other one it's going to be 2x plus 1, x plus 3. How about 2x minus 1? I bet that will work better for us, 2x minus 1. Okay, so now that all these are factored, we got a better idea. And this next one, because x plus 5 is in the top and bottom, that is not going to be a vertical asymptote, but we still have this x plus 2, so that would be x equals negative 2. In this next one, we have the x minus 3s. Those won't work, but we do have this one, so that's x minus 3. In this last one, there are no vertical asymptotes because the only one that's in the denominator is also in the numerator. So let's skip one for a second. A removable discontinuity, remember, that's one where you have a line and there's just a hole right at that point. That's if there is a 0 in both numerator and denominator. So if that's the case, we're going to find a removable discontinuity. In this case, we do not have one. In this one, we do have one at negative 5. That is because both on top and bottom. Same thing here with x equals 3, and same thing here at x equals negative 3. So those are all going to be whole or point or removable discontinuities. Horizontal asymptotes, we have a 3-part rule here, if you remember. This is if the denominator is greater than the numerator, and I'm talking about the degree of the function. So if the degree is higher in the denominator, then it goes to y equals 0. If it's the same, then, if the denominator and numerator have the same degree, then it goes to the ratio of the leading coefficients. And if the denominator is less than the numerator, it does not have one. It does not have a horizontal asymptote. So in this first example, you'll notice that the degrees are the same top and bottom, but the leading coefficients is 2 over 1. So I will say that the horizontal asymptote happens at y equals 2. And the next one, degree is the same as well, but the leading coefficients are both 1. That is the same exact thing for this one. Squared, squared, but leading coefficients are both 1. And then the last one, because the degree is higher in the numerator, we are going to say that it does not have a horizontal asymptote. All right, x and y intercepts, we got to split those up into 2 different parts here. X intercepts are set y equal to 0, solve for x. Lots of times in these problems, what that means is the zeros of the numerator. You have to be careful that it's not a removable one like we have sometimes with these. So you'll see that it doesn't always work as a 0 in the numerator, but that's often the case. So in this first one, we would get that x would be, it'd be 1/2 for that first one. In the next one, we would get 0 for that one. This one we would get 4, 0. And the last one we would get 1/2 again, as long as I factored that right. Y-intercepts, that one you set x equal to 0 and solve for y. Okay, so in this case we would get 0, 1/7. In this case we get, we get 0, 0. This one we would get 12, negative 9, so it'd be negative 4/3. And in the last one, negative 3 over 3, we would get negative 1 for ours there. Domain. Domain, in these cases, is basically make sure that 0, we don't have the 0 in denominator. Make sure no 0 in denominator. Okay, when you have 0 in the denominator, that is a big no-no. Okay, that's where we run into an issue and you can't have that as a possible x value. So in this case, we're looking at basically a combination of both removable discontinuities and vertical asymptotes. So domain for this one, we are looking at the numbers from negative infinity to 7, and then from 7 to infinity. And the next one, just to ease up here, I'm not going to write this in limit, or excuse me, in interval notation. I'm just going to say x cannot equal -5 or -2. What that would look like is from negative infinity to -5, from -5 to -2, and from -2 to infinity. You can see that that can be painful to write out every time. In this case, we could say that x cannot equal plus or minus 3 because of these two values right there. And the only one here is we can't have x equaling -3. Range, not much you can do, but you're just going to have to graph. And we've talked about graphing the range before. I'm not going to take any more of your time today going over the range. Remember, it's all possible y values. So you're just looking at, does the function hit every single y value? As for end behavior, okay, using limit notation, what we're looking at here is we're looking at a combination of two things. First of all, we're looking at horizontal asymptote. And if it has an horizontal asymptote, that will tell us a lot about end behavior. Remember, we're looking as the limit as x approaches infinity and the limit as x approaches -infinity. So what's happening to the function at those two times, at the far left and far right? So for the far left here, what we're going to do, we're going to say that the limit as x approaches -infinity, this does have a horizontal asymptote, so it's going to reach that. It's going to get closer and closer to 2, and that happens for both positive and negative versions here. In both cases, the y value is going closer to 2. Same thing for the next two. The limit as x approaches -infinity, f of x is equal to 1. The limit as x approaches infinity, f of x is equal to 1. Same thing here as that one, because the horizontal asymptotes. Now, if the horizontal asymptote is none, which means that the degree on the top is higher than the degree on the bottom, the best way to go about solving this after this is something called a slant asymptote. So since it doesn't have a horizontal one, it has a slant asymptote. This happens when the degree in the numerator is greater than the degree in the denominator. What we have to do to find the slant asymptote is long division. You're going to divide whatever your function is. So in this case, we would do, let me do it down here so we can actually do it, x plus 3, and we would take 2x squared plus 5x minus 3. Whatever your function, your quotient is, minus the remainder, we don't worry about the remainder, this is going to be your slant asymptote. That's basically where the function goes at the ends of the graph. So in this case, I'm going to get 2x, and when I multiply 2x, I get 2x squared plus 6x. Subtract, I get negative x minus 3, which is just minus 1. In this case, we get a wonderful remainder of 0. And this 2x minus 1 is our slant asymptote. What that means is at the end of the graph, if I were to graph this, we don't know what's going to happen in the middle of the graph, but by the end, if I were to graph the line 2x minus 1, that is the asymptote, meaning that the function will eventually get closer and closer, but never quite touch that value there. So it works just like a horizontal asymptote, except it's slanted. In this case, it is a straight line. Sometimes, for instance, if I randomly had one here, if I had 3x cubed minus 4x squared plus 5x minus 10, and I divided that by x plus 4. This is a function that might actually, I can tell right now, it's not going to give us a it's not going to give us a straight line for our vertical or slant asymptote. So to graph this, long division wise, I get x plus 4, 3x cubed minus 4x squared plus 5x minus 10. And what we have here would be, when I do long division, I would get 3x squared, and that would give me 3x cubed plus 12x squared. When I subtract that, I get minus 16x squared. Bring down the 5x, that'd be minus 16x. Minus 16x, minus 16 is 64. That's negative. And when I do that, that gives me positive 69x plus 69 will give me 69x minus 10. And 69 times 4, gosh, I don't know what this number is, but that's just going to be our remainder. The important part is this is our slant asymptote, so that actually means when I graph that, it's going to look like this. And I don't know what the function looks like in the middle here. It could do all kinds of weird things. Let me do it in a different color. Weird things in the middle, but eventually it's going to get closer and closer to that slant asymptote. All right. So once you have this value, what you're going to want to do is use your chart that I talked about earlier. Remember odd, even, positive, and negative. Odd positive would look like this. Odd negative would look like that. Even both up, negative both down. And you would figure out which one it is, and that will tell you what type of end behavior you're going to put here. So in this case, our end behavior, our slant asymptote was 2x plus 1. So that is odd positive, meaning it's going to start negative and end positive. So I would say that the limit as x approaches both positive and negative infinity, f of x would be positive and negative infinity. It's going to match whichever one is. All right, everything else is a review of, no, let's just do a few more. Multiplicity, 1 through 5, and then that should be enough for us today. So possible factorizations. Since I see it crosses here, I'm going to put an x plus 3 here at 1, that'd be x minus 1, and at 4, that'd be x minus 4. So that's a possible factorization or equation for that problem. The next one, since this bounces at 2, I'm going to put x plus 2, but it bounces, so I'm going to square it. It goes through here at positive 1, so that's x minus 1, and it goes through here at 3, so that'd be x minus 3. The last one here, x plus 2, square it because it bounces, x minus 1. This last one, you can see it almost looks cubic, so I'm going to do x minus 1 cubed. All right. I can do this in opposite order by graphing it. So it says it has zeros at -5, at -1, at 2, and at 4. So I have all my zeros here. All together, if I multiply these out, 2, 1, 3, 2, that is a total of 8. So that's even multiplicity. I'm going to go ahead and guess that this is positive even. There's no way to tell whether it's positive or negative. So I'm going to start up top here because it's positive even, so I said it. And I'm going to bounce at -5. I bounce because of a multiplicity that's even. I'm going to go through at -1, that's cross. At positive 2, I'm going to do a kind of weird cross that is looking cubic, and then again it bounces at 4, and I'm done there. So it ends positive as well. So that's a good sign. Positive, even, they should both be going up. All right, pretty good there. I think that should do it for us. Taking a look at what's on the quiz here, that should answer all of your questions needed. Real quickly, if I had a function, just as a review, with a vertical asymptote at 4, x equals 4 here, I would say the limit as x approaches positive, or excuse me, as it approaches 4 from the left, remember that little negative sign means 4 from the left, this value is going to negative infinity because it's going downwards, it's pointing down here. Meanwhile, if I said the limit as x approaches 4 from the right, I put a plus sign there, that would be going to positive infinity because as you see, this is going more positive on the right side. That should get you prepared for this test. All right, let me know if you have more questions. That should be good.